Hello, hello. I need like a welcome line like Carol Baskin has, like, hey all you cool cats and kittens. I guess I'll call you the COVID chemistry cadets. And your fearless leader has contracted COVID. And so I won't see y'all till next Wednesday at the earliest. So, between now and then, I want to finish chapter 11. That way, when I do see you, we can work more example problems, whether it's chapter 10 or chapter 11, and kind of get prepared for our first exam that I can have to continue to push back. So, after this, we're going to have to be on our toes so that we can get y'all 4 tests in so that you have a drop exam. Alright, so enough about that. Let's look back at your PowerPoint. I believe this is slide 23. Yes, so we've talked about intermolecular forces. Now let's talk about some properties that depend on intermolecular forces. The first is going to be solubility. So solubility, it depends on your forces of your solute and your solvent. Okay, remember, solute is what you're mixing with your solvent, but your solute, by your book definition, is present in a smaller amount. Your solvent's present in a larger amount, but I don't love that definition. I like to say your solute is what you're dissolving, whether it be a liquid, a solid, or a gas, and your solvent is your dissolving medium. Okay, so as far as solubility goes, like dissolves like. So basically, if your solute and your solvent have the same intermolecular forces present in each of them, they'll likely dissolve each other. For example, polar substances dissolve in polar solvents. Okay. Another word we use to talk about solubility is miscible. That's just when you have 2 liquids. So a miscible liquid will always dissolve. Miscible liquids always dissolve in each other. Let me talk about that in a few later slides. Then again, polar substances dissolve in polar solvents, nonpolar, and nonpolar solvents. Okay, so really you're just looking at the intermolecular forces. If they have similar intermolecular forces, they're likely to be soluble in one another. Oh, my chemistry guy is back. He said, why did the bear dissolve in water? Because it was polar and water's polar. That funny guy. Alright, so let's look at what's happening here. So this just shows hydrogen bonding. This is a worthless slide. I really need to edit this PowerPoint. It says it shows hydrogen bonding in water and ethanol, but I only see ethanol here, so there's that. You can see that your ethanol is polar. Here, let's look right here. It actually has hydrogen bonding. That hydrogen bonding interacts with one another. So you have hydrogen bonding as your intermolecular force. So if I were to try to dissolve ethanol, that's what this is, in water, it would dissolve because water also has hydrogen bonding. Okay, so they would just orient themselves so that the positive and negatives aligned. So the basis behind this, and I think we talk about this somewhere, is in order for them to dissolve, your solute, let's write that down, solute interactions must be broken, and your solvent interactions have to be broken. This will only happen if your solute solvent interactions are stronger than each of these, or approximately the same. Okay, because I'm not going to break a strong interaction to go form a weak interaction or a weaker interaction per se. I think it's the next chapter we might talk about that. All right, so I believe the next slide talks about immiscible liquids. So an immiscible liquid is just one that basically your two liquids don't dissolve in each other, so you have two layers. It's like oil and water. The less dense is on bottom. Less dense is on top, more dense is on bottom. An example would be pentane, who is a nonpolar molecule, and water, who is polar. They are immiscible because water is not going to break its hydrogen bonding with itself down here to form a bond with this pentane, who has no hydrogen bonding. Okay, so they don't mix. They're called immiscible. If they do mix, they're miscible. So this is just referring to liquid. You have a liquid solute, a liquid solvent. Surface tension is another one, and I meant to pull up something to show y'all. If I have to make another part for this, I'll pull it up then. All right, so what is surface tension? Surface tension is the property of a liquid that results from the tendency of the liquid to minimize its surface area. So to minimize surface areas, liquids form drops so that they're spheres like this in a gravitational field. The reason they do that is because they can interact with themselves more if they're in a sphere like this, rather than if they're like in like a straight little puddle or something. Okay, so that also means that the interaction with the outside is kind of less than it would be if it was not in a spherical shape. The spherical shape is going to be the most bang for your buck, I guess you'd say. You're going to get the most interaction with the molecules within that sphere than the interactions with the outer world. I hope that made sense. So, the surface tension of a liquid is the energy required to increase the surface area by a given amount. So, how much energy is it going to take for me to pull these particles apart in this sphere to make, say, this rectangle sphere, oblong sphere? Okay, that's what surface tension is. The stronger your intermolecular forces, the higher the surface tension. So it's going to be harder to break those intermolecular forces to increase your surface area. And that should make sense. A stronger the intermolecular force, the more energy required to break apart that force. So raising the temperature of a liquid reduces its surface tension, because when you raise the temperature, you're breaking your intermolecular forces. That's why a paper clip, if you place it very carefully in a puddle of water, it will float. Another characteristic affected by intermolecular forces is viscosity. And you don't need to know any of these units. It's just there in case you wanted to know. The stronger the intermolecular force, the higher the liquid's viscosity. So, the more spherical the molecular shape, the lower the viscosity, because it's easier for it to flow. Raising the temperature reduces its viscosity. So by raising the temperature, you break intermolecular forces, so it's easier for it to flow. So viscosity basically is the resistance of a liquid to flow. Okay. So that's why stronger intermolecular forces have a higher viscosity. Okay. Another one is capillary action. Capillary action is something we've talked about in lab. It's the ability of a liquid to flow up a thin tube against the influence of gravity. The liquid rises up the tube until the force of gravity counteracts the capillary action. So the narrower the tube, the higher the liquid will rise. Capillary action is a result of two forces working in conjunction. It's your cohesive and your adhesive forces. So cohesive forces hold your liquid molecules together. Adhesive forces attract the outer liquid molecules to the tube surface. So if both of those work together, it'll pull that liquid up that thin tube, because you have your outside molecules attracted to the glass, your inside molecules attracted to each other, so it's holding the liquid together, and it'll draw up that tube. Another property affected by not only intermolecular forces but cohesive and adhesive forces is meniscus. So your a meniscus, if you don't know, I hope you know, is the curving of the liquid surface in a thin tube due to the adhesive and cohesive forces, just like you have in a capillary tube. So the meniscus of water is concave, meaning it does like this. You can kind of see that down here. In a glass tube, because water adhesion to the glass is stronger than the cohesion to itself. So these molecules here stick to the glass more than they stick to one another. Mercury's meniscus is the opposite. It caves up, as you can kind of see right here. That is because Mercury's cohesion to itself is stronger than the adhesion to the glass. So it kind of forms a half sphere, you see, to keep those interactions together. Metallic bonds are stronger than any intermolecular force. Metallic chemistry is its own subset of chemistry. Most people don't even get into that unless you go to grad school. It's pretty complex. Okay, so that is all of our properties that are affected by intermolecular forces. Now we're going to look at in the interconversion of our liquids. And it, of course, has to do with breaking intermolecular forces. So we're going to look at going from solids to gases, solids to liquids, liquids to gases, etc. This slide, again, is one of those ones that won't print. If you print out the PowerPoint, it prints blank. But I encourage you to take this slide and remember these words and maybe add to them as we go. Because on your test, I'll use these words, and sometimes y'all aren't sure if they go from, say I say condensation. Y'all aren't sure if that's liquid to gas or gas to liquid. It trips you up for some reason. Okay, so make sure you're familiar with that. All right, so the first one we focus on is vaporization or evaporation. All of them are like the same basis of vaporization. So I think, if I remember correctly, I'll spend a good bit of time talking about vaporization at the molecular level, and then we're going to apply that to all the other phase changes. Okay. So first off, vaporization is when you're going from a liquid to a gas. So if I had an open container and I left it sitting undisturbed, evaporation continues until the liquid, all of the liquid, is converted into a vapor. So over time, all of your molecules break free from your liquid and they become a gas. You can test this out if you'd like. Leave something, get you a glass of water and leave it sitting for a while. I'm not saying it's going to happen overnight. I'm just saying eventually it will happen. In a closed container, though, the process of vaporization is countered by the process of condensation. So those are two opposite processes. And so it'll start vaporizing, your liquid will start vaporizing, but then the vapors will get trapped back in the liquid. So then they'll start condensing. So you can also always, if you look at a water bottle that's been setting undisturbed, you'll have beads of water at the top, and it's kind of foggy. That's because vaporization and condensation are happening simultaneously, and they've reached something called a dynamic equilibrium.